Hello everybody. Today we are going to be talking about reducing size and increasing efficiency with the disruptive technology of silicon carbide. My name is Brandon Becker. I'm the product line manager of wide bandgap here at ON Semiconductor. As always, for more information, you can visit our website, www.onsemi.com. We even have our own URL if you do a /wide-bandgap. Today we're going to be going over ON Semiconductor's SiC ecosystem. I'm going to present a few slides on our modeling, a quick view of our portfolio, and I'm going to dig into a couple applications, specifically high voltage auxiliary power, some PV charging and renewable energy applications, and lastly, power supply applications, including the PFC and LLC stage. At ON Semiconductor, we're really big on the wide bandgap ecosystem. So we want to provide a full systems solution for our customers. This includes SiC diodes geared towards ruggedness, SiC MOSFETs geared towards ruggedness and speed, dedicated drivers for wide bandgap devices, as well as our FIT design modeling technology for SiC and GaN power devices. So for our SiC modeling is very important. It's very important to build one model that works in any simulator. This reduces modeling work for the engineers, and it provides consistency between simulations and devices. The models must be physical, intuitive, and predictive, and above all, accurate. So you can see a list of the following simulators that our models work on. So we'll go into these models. Well, we take a lot of our process parameters and put them into our models. This includes gate oxide thickness, shield oxide thickness, gate length, shield length, and our doping profiles. So all of our process information goes directly into our models. From a die perspective, we put in the chip width, height, gate runners, pad height. We put in our patented edge termination, gate runners, and gate pads. So all this information from our process and our die go into our models, and now let's see what we get out of our models. So we get a bunch of different output characteristics, including static current over voltage, and so you can see here the measured versus simulated outputs. We can model different temperature behaviors, again across drain currents, across thresholds, across RDS-ons. And once again, you can see how accurate our models are on the measured data versus our simulated data. We can also model different capacitances. So for complex circuits, which are strongly dependent on different device capacitances, we can model these COSS, CISS, CRSSS, and so you can see once again how our simulations and our simulations and our measured data compare. And then we can take it one step further, and we can use these models in dynamic tests. So we can use these physical models in DVDT and DIDT with different gate voltages to predict switching losses, study EMI, and study gate driver power loops. So you can see that this was done in a double pulse test dynamically at 25 degrees C and also at 175 degrees C. And lastly, this is very powerful to work with engineers because it's a very scalable modeling system. So for example, if you want to evaluate a certain die size given a certain RDS-on or a certain current rating, you can look at what's available on our portfolio. We can give you a model, and then we can scale that model so that you are doing a majority of your design work in simulation, and that way when you get parts to test in the lab, which is the most time consuming, you know already beforehand the results that you should expect to see. So this scales very well across charge, QG, RDS on, and all the different capacitances. Okay, so now let's talk a little bit about ON's SiC portfolio. If you look on the upper left-hand side, you'll see that we have 650 volt, 1200 volt, and 1700 volt diodes available. We have them available in different packages from TO220 all the way to D2 pack and QFNs. We then take those die and we put them into a variety of different modules. These modules are going to be hybrid SiC modules where we take our IGBTs and our SiC diodes and integrate them into a different power module. On the bottom side, you can see that we are in development with 650 volt MOSFETs. We have released our 900 volt MOSFETs, our 1200 volt MOSFETs, and are in development with our 1700 volt MOSFETs, and again, a variety of different discrete packages. We then take those MOSFETs and then proliferate into our modules as well. And so on the bottom right-hand side, we have a variety of different full SiC modules, some orientated towards automotive, while others are orientated towards different industrial applications. Overall, we have a very wide and big breadth of portfolio and have solutions for every different application that you're going to run into. Okay, let's take this and dive in and look at how these parts are affecting industrial SiC applications. One area where SiC really makes a good solution is the high voltage auxiliary power. So we have all the motor drive, UPS, solar inverters, elevator systems where the DC link voltage is anywhere from 300 volts up to 1,000 volts. And then we need to tap into this to run all the secondary systems. So this would be an aux power supply where we can have a high voltage input. So there are a couple different high voltage switch technologies that could be used. For example, we could use IGBTs and MOSFETs. They have the blocking voltage they need, but they also have high conduction and switching losses. We could use two silicon MOSFETs in series. Once again, they have the blocking, but they have high RDS on, low switching frequency, and complicated driving circuits. We have a trademarked solution with a ESBC, which is emitter switched bipolar MOSFET. This gets very good efficiencies, so high efficiency, around 84% at 300 volts, but some limitations are complicated drive circuit, limited switching frequency. And so now we have the availability to use SiC MOSFETs. These have the blocking voltage needed for this application, as well as low RDS on, the ability to run at high frequencies, and they are easy to drive. So here's a board comparison between an ESBC running at 75 kilohertz versus a SiC solution running at 300 kilohertz, which now you can see it's half the size. It's much lower dimensions, so smaller height and width, as well as provides 20% higher power. A couple things to notice are your input and output capacitors have changed dramatically, and also the magnetics changed dramatically. So your transformer can be optimized to run using SiC MOSFETs. And then we can take a look at the results. So at a 300 volt input, we get about a 3% higher efficiency. And even moving up to 600 volts, we still get a higher efficiency, although due to the windings, we would want to move up to a 1700 volt solution to get an even better efficiency with a higher voltage input. Overall, though, you can see the much smaller size, the less component count, and the higher efficiency that this solution provides. Next, we'll go into general industrial applications where we use active rectification or PFC. If you look, we have different modules and discretes available. Typically, this is going to be a 3-phase PFC rectifier. You can see on the bottom left is a solution using superjunction MOSFETs coupled with SiC diodes or IGBTs with silicon diodes, which we have solutions for those. But moving over to the right, we have a SiC MOSFET solution, which provides the highest performance and provides bidirectional performance. So you can go both ways through that rectifier. We have a similar solution on the DC-DC and output stages. Again, using IGBTs and SiC diodes together, we have those solutions for low costs. But on the right side, we have standalone SiC MOSFETs, which again can be used for the best performance and the higher power levels. And finally, we'll talk about the server industry. The server industry has changed a lot. This is where you'll see an input voltage from 220 to around 230 volts AC and an output voltage of 400 volts DC. The conventional solution using silicon PFC is typically a CCM or continuous conduction mode solution or a dual boost, as well as a full bridge. Some disadvantages to this is that it is basically impossible to get above a 95% efficiency rating. You have limited switching frequency with 2 inductors, and you have a high component count, which creates a larger footprint. The trend is using SiC to enable a PFC solution, and this is typically seen as a totem pole solution. So advantages is we can hit 98 to 99% efficiency. We can increase the frequency, increase the power density, have a bidirectional power flow, and reduce component count. So we joined forces with Cilantro Semiconductor, and we created a 80 plus titanium 1.2 kilowatt totem pole PFC using Cilantro's SA8000 and totem pole PFC controller, along with ON Semiconductor's SiC MOSFETs. This one specifically used our 60 milliohm 900 volt SiC MOSFETs. We were able to create this, which meets the 80 plus titanium standard, and we are able to reach an overall 99% efficiency and provide optimal switching patterns, reliable startup, and a very high power density. Some additional advantages is that you have a dedicated totem pole controller with direct current hysteresis control and overcurrent protection. And again, this was a joint development with Cilantro, and we have it optimized for ON Semiconductor's SiC MOSFETs. So that will conclude today. Thank you, and as always, if you have any additional questions, comments, please feel free to visit our website at onsemi.com. Thank you.